A particle races through the vacuum, swift, precise, following a clear, unwavering trajectory. But now, imagine the same particle stretched across space like a mist, crossing all possible paths at once, interfering with itself, no longer a point, but a shimmering vibration. So, what is it? A particle? Or a wave? Welcome to the world of quantum mechanics, a place where logic falters, where the mere act of observation can rewrite reality, and where the laws of nature seem to play a mysterious game of hide and seek. Here, one of the most electrifying questions in science merges. How does a quantum particle decide whether to act like a wave or a particle at any given moment? This is not just an abstract paradox. It strikes at the heart of everything we think we know about matter, about information, even about the fabric of reality itself. The answer could change it all, from the architecture of the atom to the mysteries of consciousness. For over a century, experiments have only deepened the mystery. We've seen electrons pass through two slits at once, photons behaving differently depending on whether they are watched, even future events reaching back to touch the past. It sounds impossible. But these are not theories. They are experimental facts. At first glance, the setup seems deceptively simple. A device fires electrons toward a plate with two slits. Beyond it, a screen captures where the electrons land. Common sense suggests the electron should pass through one slit or the other, striking the screen like tiny bullets and forming two bright lines. But reality had other plans. When scientists do not observe the electrons, they behave like a wave spreading out, passing through both slits simultaneously, creating an interference pattern of alternating dark and light bands, the same kind of pattern you'd see if ripples on water passed through two gaps and overlapped. Somehow, the electron, a particle with mass and energy, acts like a ghostly wave, yet place a detector by the slits simply to find out which path the electron takes, and everything changes. The wave vanishes. The electron collapses into a particle, choosing one slit, leaving behind only two bright bands, and the interference disappears. A simple act of observation, gathering just a fragment of information, alters the nature of reality itself. Physicists were stunned, not because the results were strange, but because they were consistent. Every time, with electrons, with photons, with atoms, even with enormous molecules like C60 fullerenes, molecular giants by quantum standards. The deeper the scientists dug, the stranger the world became. A single particle could spread across space, dance through two paths at once, and yet snap back into a solid reality the moment we looked. And even more incredible, this behavior persisted even when particles were fired one at a time. No crowd effect, no group creating a wave. Each individual particle alone, one after another, somehow knew how to create the interference pattern, as if whispering across time to itself. The double-slit experiment shattered our very notion of what it means to be real. How can something tangible, something with mass and energy, behave like a weightless cloud across all of space? And why does the simple act of observation collapse this cloud into a definite solid object? This puzzle stands even today as a towering riddle at the heart of quantum physics. And behind it looms a deeper, unsettling question. How does the particle know it's being watched? In our everyday experience, observation is passive. We gaze at the sky, the ocean, the people around us, and the world remains indifferent to our glance. But in the quantum world, observation is no passive act. It is a force, an intervention capable of twisting the rules of reality itself. Here, to look is to touch, to watch is to shape. Back to the experiment. When unobserved, the particle exists in a shimmering world of probabilities moving through every possible path at once. But the moment we try to know, even by the gentlest measurement, the shimmering world collapses. Simply the potential to obtain information, even without any direct interaction, is enough to change the destiny of the particle. Scientists tried every trick they could imagine, detectors that could register particles without recording the information. And still, if no information was available, the interference persisted. It wasn't the machine, it wasn't the detector. It was the mere possibility of knowing, as if the particle wasn't just reacting, it was understanding. This isn't just physics anymore. It's almost the psychology of elementary particles. And it leads us to a profound and eerie question. Could consciousness and information be woven into the very fabric of the universe? Some interpretations of quantum mechanics suggest exactly that. A particle remains suspended in all possible states, a superposition, until an observer collapses it into a single reality. But then, what counts as an observer? Does it have to be a human mind? Is a machine enough? Or is the very potential for information all the universe needs to choose? Here, quantum interpretations diverge. The Copenhagen interpretation, the most famous, claims that reality remains undefined until measured. A particle is just a cloud of probabilities until an observation forces nature's hand. But other ideas beckon. The many worlds interpretation suggests that every quantum event spawns new universes. In one world, the particle passes through the left slit. In another, the right. All outcomes happen, just in different branches of the infinite multiverse. There's also the de Broglie-Bohm theory, proposing that particles always have definite paths. But those paths are guided by an invisible wave, a ghostly field of probabilities. All these theories wrestle with the same astonishing fact. Reality, at its deepest level, is far stranger and more fluid than it seems. And the questions grow stranger still. If observation can change the behavior of particles, could it be that consciousness itself is fundamental to reality? Is consciousness woven into the same cosmic fabric as space, time, and energy? For decades, such ideas were dismissed as philosophy. Today, they are taken seriously by physicists, philosophers, and information theorists alike. Because in a world where particles behave like thinking entities, the boundary between observer and observed begins to dissolve. And it gets even stranger. Experiments have shown that interference can be restored even after the information about a particle's path is erased, after the particle has passed through the slits. These are the quantum eraser experiments. Imagine a particle has already made its choice. But if we later erase the record of which path it took, the interference returns, as if the particle retroactively rewrites its past, as if your own past life could change simply because someone today deleted the memory of it. It is breathtaking and even more unsettling. Some experiments suggest that choices made in the future can influence a particle's behavior in the past. This challenges everything we think we know about time. In the quantum world, The future can rewrite the past. Cause and effect become fluid, almost interchangeable. Thus, the double-slit experiment is not merely a bizarre footnote of physics. It is a portal, a glimpse into a universe where information is more fundamental than matter, where reality is not fixed but malleable, and where consciousness might be far more powerful than we dare imagine. And in this mysterious, shifting world, one final question echoes. Who are we in this universe? Mere watchers on the sidelines, or actors, participants in a grand cosmic play where the very act of observing brings reality into existence?